Everyone assumed sodium batteries were a science project, a curiosity sitting in a university basement while the real money, the real infrastructure, and the real future was built around lithium. That assumption just died. On the 27th of April, 2026, CATL signed the largest sodium-ion battery order in the history of the industry. 60 gigawatt-hours, 3 years, 1 contract. And here is what that number actually means, because most of the coverage you have seen gets it wrong. 60 gigawatt-hours is not a pilot program. It is not a demonstration project. According to CATL's own annual report, their total energy storage battery sales for all of 2025 were 121 gigawatt-hours. This single contract, with a company called HyperStrong, equals half of everything CATL shipped to the entire world in energy storage last year. In one deal, for one chemistry that the industry was writing off as uncompetitive just 36 months ago. Industry observers, including writers at Electrek, have already called this a potential deep-seek moment for global energy storage. That comparison is not hyperbole, it is a warning, and by the end of this video, you will understand exactly why. But before we get to what this means for the United States, for the grid, for every EV maker who spent the last decade betting everything on lithium, there is a question that needs to sit in the back of your mind for a few minutes. The number you have probably seen on social media says sodium-ion batteries cost somewhere between $10 and $19 per kilowatt-hour. That figure is everywhere. It is also completely fabricated. Nobody at CATL ever said that. No battery manufacturer on Earth is selling at that price. Where did it come from, and what does the real cost number tell us about whether this breakthrough is genuine or just another overhyped press release? We will get to that. But first, you need to understand why lithium earned its dominance in the first place. Because the story of why sodium lost is the same story as why sodium is now winning back. In 1972, a chemist named Stanley Whittingham, who would eventually receive the Nobel Prize, discovered that lithium ions could move in and out of titanium disulfide electrodes at room temperature without destroying them. That was the foundational insight behind every rechargeable lithium battery ever built. What made lithium so dominant was not just chemistry, it was geometry. Graphite, which became the standard anode material when Sony commercialized the lithium-ion cell in 1991, has a layered crystal structure. Those layers are stacked with gaps of almost exactly the right size to accept a lithium ion, which has a radius of about 76 picometers. Lithium slides in, lithium slides out, thousands of times, and the structure survives. Sodium is a different story. Sodium ions are 102 picometers in radius. That is 35% larger than lithium. When you push a sodium ion into a graphite structure, it does not fit cleanly. It wedges itself between the layers and forces them apart. After a few hundred cycles, the anode is physically damaged. The gaps have been stretched beyond recovery. The capacity collapses. This is not a manufacturing problem. It is not a quality control problem. It is basic crystallography, and it meant that when the industry chose graphite as its standard anode in the early 1990s, it was simultaneously choosing lithium and rejecting sodium for the next 3 decades. Approximately $1 trillion of manufacturing infrastructure, supply chain, and intellectual property followed that decision. Sodium researchers had a theoretical answer. Hard carbon. If you take an organic precursor, something like biomass, tree resin, or glucose, and heat it to between 1000 and 1400 degrees Celsius in an oxygen-free environment, you get a material whose structure is permanently disordered. No clean crystal layers. Instead, a chaotic landscape of nanopores and irregular gaps where sodium ions, in spite of their larger size, can settle and store charge reversibly. Around the year 2000, researchers at Dalhousie University in Canada confirmed that hard carbon could host sodium ions in a way that survived repeated cycling. The finding was real. The problem was timing. The industry had already committed, and a discovery in an academic journal does not move a trillion-dollar supply chain. CATL made a different decision in 2016. They launched a dedicated sodium-ion research program, committed approximately $1.5 billion over the following decade, assembled around 300 researchers, and built and tested roughly 300,000 individual cells. What they were solving was not the fundamental electrochemistry, which Dalhousie had already cracked in principle. They were solving the manufacturing problems that nobody had bothered to solve because nobody had been willing to pay for the solution. The first problem was moisture. Hard carbon is porous by design. Those same nanopores that hold sodium ions also absorb water vapor from the air during manufacturing. Water traces react with the electrolyte and produce gas inside the cell. The gas destroys performance. CATL's solution was to chemically replace the hydrophilic surface groups on the carbon, the ones that attract water, with hydrophobic compounds that seal the pores without blocking them for sodium ions. The second problem was dimensional control at the angstrom scale. The pores need to be just wide enough for sodium to enter and just narrow enough to maximize charge density. Too wide and you lose capacity. Too narrow and ions cannot move freely at high charge rates. The third problem was the current collector. In a lithium cell, lithium alloys with aluminum, which means you have to use copper foil on the anode side. Copper foil is expensive. Sodium does not alloy with aluminum. That means CATL could replace copper with aluminum across the entire cell, reducing the cost of the current collector by roughly 70%. That last detail is important because it is part of the reason sodium cells will eventually be cheaper than lithium cells to manufacture, even though they are not cheaper today. And that brings us back to the number you saw online, the $10 per kilowatt-hour figure. Here is exactly what happened. Sodium carbonate, the raw material, costs roughly $200 per metric ton. Lithium carbonate, the equivalent raw material for lithium cells, has been as high as $80,000 per ton and currently sits around $26,000 per ton after a collapse of more than 80% from its 2022 peak. Someone looked at that raw material price gap, did a naive comparison, and concluded that sodium cells must cost almost nothing. The calculation ignores the fact that raw material is only a fraction of cell cost. You still have to synthesize the cathode material, coat the electrodes, assemble the cell, form it, test it, and run a factory. According to Wood Mackenzie, one of the most respected energy consulting firms in the world, the actual cost of sodium-ion cells in 2025 was approximately $59 per kilowatt-hour. Lithium iron phosphate, the chemistry used in most Chinese EVs and grid storage systems, was approximately $52 per kilowatt-hour. Sodium is currently more expensive than the lithium it is supposed to replace. Wood Mackenzie does not expect sodium to reach cost parity with lithium until around 2035. The $10 number is a myth. Sodium is not winning on price right now. So why is CATL signing a 60 gigawatt-hour contract? What do they know that the price per kilowatt-hour comparison misses completely? This is the part of the story that almost nobody is covering correctly. The reason CATL is betting on sodium right now is not because sodium is cheap. It is because of three specific failure modes of lithium that have nothing to do with price and everything to do with physics. The first failure mode is fire. Lithium-ion electrolytes use organic solvents as the medium through which ions travel between electrodes. Those solvents are flammable. When a lithium cell is punctured, overcharged, or subjected to excessive heat, those solvents ignite. Once one cell ignites, the heat triggers the adjacent cell, which triggers the next, in a cascading process called thermal runaway. In New York City alone, the FDNY recorded 267 fires caused by lithium-ion batteries in 2023, resulting in 18 deaths and 150 injuries. Since 2022, lithium-ion batteries have caused more than 800 fires, 30 deaths, and over 400 injuries in New York City, according to FDNY data. Lithium-ion battery fires have replaced electrical fires as the leading cause of fatal fires in New York City, surpassing both cooking accidents and smoking-related fires. The majority of these fires started with e-bike batteries overheating in apartment buildings, but the same thermal runaway mechanism exists in every lithium cell, regardless of application. CATL's Naxtra sodium battery passed China's most demanding safety standard, the GB 3803 1-2025, which requires cells to survive needle penetration, crushing, and saw blade tests without catching fire or producing smoke. The Naxtra passed all of them. That is not just a marketing claim. It reflects a fundamental difference in the chemistry of the electrolyte. The second failure mode is cold. The American Automobile Association tested 5 electric vehicles in conditions at 20 degrees Fahrenheit with the heater running and found an average range loss of 41%. One vehicle in that study lost 50% of its range. An AAA study updated in 2026 continues to show losses around 39% at 20 degrees Fahrenheit. The mechanism is straightforward. At low temperatures, lithium ions move slowly through the electrolyte. They cannot intercalate into the graphite anode fast enough during charging, so they plate onto the surface of the anode instead as metallic lithium dendrites. Those dendrites are sharp. They grow inward through the separator, the membrane that keeps cathode and anode apart, and when they reach the other side, they short-circuit the cell. Cold weather does not just reduce range temporarily, it permanently damages the battery over time. CATL's Naxtra retains 90% of its capacity at -40 degrees Celsius. At -30 degrees Celsius, it delivers nearly 3 times the discharge power of an equivalent lithium iron phosphate cell. It continues functioning at -50 degrees Celsius. For any grid operator trying to store renewable energy in the northern United States, Canada, Alaska, or any mountainous region, that specification is not a marketing slide. It is the difference between a battery that works in January and one that does not. The third failure mode is supply chain concentration. 3 countries, Australia, Chile, and China, control approximately 90% of the world's mined lithium. China processes around 65% of battery-grade lithium and manufactures roughly 75% of all battery cells globally. Between 2020 and late 2022, the price of lithium carbonate went from roughly $10,000 per ton to over $80,000 per ton, an increase of more than 700% in less than 2 years. It then collapsed, losing more than 80% of its value by 2023, according to Benchmark Mineral Intelligence, before rebounding to around $26,000 per ton at the beginning of 2026. Every car company, every grid developer, every utility that signed long-term lithium supply contracts in 2021 or 2022 paid the peak price. Sodium is one of the most abundant elements on Earth. The raw material is not subject to the same geographic concentration or price volatility. That stability is worth something that no cost per kilowatt-hour spreadsheet captures. Now here is where the story gets genuinely surprising, and where most of the coverage has missed the technical sophistication of what CATL actually built. CATL is not positioning sodium as a replacement for lithium. They built something more intelligent. The Naxtra battery and their free-void dual chemistry architecture put sodium-ion cells and lithium-ion cells inside the same physical pack, managed by software that decides in real time which chemistry to use based on temperature, vehicle speed, and remaining charge. Sodium handles cold starts, low-temperature cruising, and any operating condition where lithium is physically compromised. Lithium handles highway driving and long-distance trips where energy density matters. The software arbitrates between them continuously. On the grid storage side, the logic is even cleaner. The sodium cell CATL, unveiled for energy storage at the Beijing Expo in April 2026, is rated for more than 15,000 cycles at 80% capacity retention, with 97% round-trip efficiency. The cell uses the same physical dimensions as CATL's existing 587 amp-hour lithium storage cell. A grid operator who already owns lithium storage hardware can switch to sodium cells without redesigning a single enclosure, a single rack, or a single electrical connection. The switching cost drops to nearly zero. That last detail is why the HyperStrong contract is real and not theoretical. HyperStrong can slot these sodium cells into projects that were designed for lithium. They can offer customers better cold weather performance, longer cycle life, and no cobalt or nickel in the cell, using infrastructure they already own. The first mass production electric vehicle with sodium-ion batteries, the Chang'an Nevo, a 6, built with a 4.5 kilowatt-hour Naxtra pack, was presented in February 2026 and is set to reach the market at mid-year 2026. It represents roughly a decade of development and approximately $1.5 billion of CATL's invested capital. The 60 gigawatt-hours of grid storage tied to the HyperStrong agreement begin shipping over the next 36 months. This brings us to the question that nobody in the American EV press is asking loudly enough. Sodium was supposed to be the technology that broke the world's dependence on Chinese battery dominance. Sodium is abundant everywhere. The chemistry does not require cobalt or nickel. The raw materials are not concentrated in 3 countries. Every argument for sodium was also an argument for a diversified global supply chain. And then this happened. According to the International Energy Agency, China currently controls more than 95% of all announced sodium-ion manufacturing capacity in the world. Not most of it, 95%. LG Energy Solution, the third largest battery manufacturer on the planet, chose to build its sodium-ion pilot line in Nanjing, China, rather than in South Korea, because that is where the manufacturing knowledge lies. Every Western attempt to build a sodium-ion industry has ended in failure. Northvolt, the Swedish company that was supposed to be Europe's answer to CATL, validated a sodium-ion cell at 160 watt-hours per kilogram in late 2023. By November 2024, it had filed for bankruptcy after burning through approximately $100 million per month attempting to master large-scale manufacturing. BMW had canceled a $2 billion supply contract with Northvolt in June 2024, citing inability to deliver. The company filed for bankruptcy in its home country of Sweden in early 2025, having raised $15 billion over its lifetime, with approximately $5.8 billion in debt at the time of filing. Natron Energy, the American company founded on Stanford University research in 2012, began production at a facility in Holland, Michigan in April 2024 and announced a $1.4 billion gigafactory planned for North Carolina in August 2024. On the 27th of August 2025, Natron's board determined that fundraising had failed. The company laid off 95 employees, ceased operations on September 3, and pursued an assignment for the benefit of creditors rather than Chapter 11 bankruptcy, allowing for a quiet liquidation of assets. The North Carolina factory was never built. The Michigan facility operated for less than 6 months. The pattern is not bad luck or bad management at individual companies. The pattern is structural. Western battery startups cannot access the combination of government support, vertically integrated supply chains, domestic market scale, and patient capital that Chinese manufacturers have built over 20 years. China holds approximately 10,000 of the roughly 14,000 sodium-ion research publications ever written. The manufacturing knowledge advantage compounds annually. Every year that passes without a Western gigafactory making sodium cells is another year of learning that only exists inside Chinese factories. So what does that mean for you, for the American grid, for every utility and developer who is right now trying to figure out where the next generation of storage technology is coming from? It means that sodium did not solve the dependency problem. It relocated it. If you were dependent on China for lithium chemistry, the arrival of sodium chemistry at scale, with 95% of manufacturing capacity still in China, does not change your strategic position. It changes the mineral. The political risk, the supply chain concentration, the manufacturing leverage, all of it remains exactly where it was. There is a window. Peak Energy in Denver has announced the first large-scale sodium-ion battery installation in the United States. Tiamat in France is working toward a gigawatt-scale factory. Reliance Industries in India acquired Faradion and is scaling production. These efforts are real. They are also nowhere near the scale of a single 60 gigawatt-hour contract. CATL just wrote one order that exceeds what the entire rest of the world can currently produce in sodium-ion cells. The technology itself is not the barrier. The barrier is everything that surrounds the technology. The supply chain for hard carbon precursors, the cathode material synthesis, the cell formation equipment, the quality control processes refined across 300,000 test cells over a decade, and the customer relationships built on the ability to actually deliver the battery that does not burn. The battery that works at -40 degrees, the battery built from one of the most common elements on Earth. That battery is real. It is in production. The first cars powered by it are rolling off assembly lines this summer, and the first grid installations from this contract will be energized within the next year. But the uncomfortable truth is this: the breakthrough is real, and the dependency it was supposed to fix is not fixed. China did not just win the lithium era. It positioned itself to define the sodium era as well, and it did it the same way it always does, not by keeping secrets, but by doing the hard, expensive, unglamorous work of building factories while everyone else was writing about the future. If this kind of analysis is useful to you, subscribe. Every video on this channel is built the same way, starting with what you think you know and ending with what is actually happening.